Today we're going to begin a rather lengthy topic, which I believe takes us 4 weeks in total. This first week we're going to do a little reading in the text, and I'll go over a summary of the topic here today. This whole topic is about the time value of money, and as I might have mentioned in an earlier conversation with you, this is really the heart and soul of finance. Many of you who've taken some accounting will have had an encounter with the time value of money before. For some of you, this may seem quite easy and simple and straightforward. For others of you, it will seem blindingly difficult and obscure. But for all of you, if you're going to have any truck with finance at all, you're going to have to come to grips with the time value of money and the mathematics involved in it and the approaches and calculations involved. So this is chapter 5 in our textbook. Now, I personally have seen over the years, too many years to recount, as a matter of fact, any number of expositions of the time value of money. I personally think that the exposition that is given in our textbook is as good as it gets. It's not bad at all. I think it works very well indeed. What we'll be doing in the ensuing 3 weeks after this week is we will be working on actual calculations, learning how to do time value of money calculations using Microsoft Excel. And I suspect that that's where you're going to really learn this stuff. But let's get going with it today and see what we can find out. So we'll start out on slide 5-2, which you can access in the Readings and Resources folder for topic 2. Here's some real-world questions that you might encounter to motivate what we're going to do in this topic. What will my loan payments be if I borrow $10,000 for 5 years? If you think you should just divide 10,000 by 5, you'll turn out to be wrong, and we'll see why. That'll give you some idea, but it turns out it'll be a pretty bad idea. What will your monthly loan payments be if you borrow $10,000 for 5 years? Which is better, 0 interest for a year or a lower price for cash today? You go out to buy a car and they say, you can have your option, 0 interest for a year on a loan that will be 5 years, or lower price if you just sell this car to you cheaper if you give us cash today.
They do that a lot too. They'll say 0 for 60 or 2,500 cash back.
That's right. As Jake observes, this is a rather popular ploy or scheme or whatever you'd like to call it for selling cars these days. How would you approach that opportunity? Well, as it turns out, if you know enough about the time value of money, you whip out your Excel spreadsheet and you make the decision with perfect confidence. These days you can actually have an Excel spreadsheet right on your smartphone if you've got good eyes. It does require good eyes, though. It doesn't quite work out for me. How much do I need to save for retirement? Now there's a question. Some people say as much as possible, but that's obviously not a very good answer, is it? So we're going to encounter some ways to think about that and some calculations you can go through. But it'll either drive you nuts or bring a smile to your face, realizing that you'll be able to retire in the lap of luxury if you just do this. All right, so how much is a loan worth? You say, what the hell does that mean? How much is a loan worth? Well, what that means is that what is a loan? Well, a loan is a financial instrument. Now, many times, these loans can be bought and sold. I mean, you might have bought a car the other day, and you took out a loan with a GMAC or somebody, and then lo and behold, you get a payment book from the XYZ Corporation. What happened? They sold your loan. That's what happened. So what do you mean, sold my loan? Well, what does a loan represent from the owner of that loan's point of view? A stream of future cash payments. That's worth something. What's it worth? How much would you pay for the loan? Well, what a question. Very interesting question, actually, if you're in finance. If you're a particular kind of finance, you might buy and sell loans by the day.
Banks do say refinancing the mortgage.
Oh, absolutely. Banks, what happens if, these days, what happens if you go to get a mortgage is the first thing is you have to sign in blood and give them rights to your firstborn or something. But after they get through with all that, when you go to get a mortgage, you're going to probably deal with a mortgage broker of some kind, and they're going to do all the paperwork for you, help you sign on the dotted line and everything. And as soon as the deal is closed, what are they going to do? Turn around and sell the mortgage to some larger organization. They were just doing paperwork. That's all they were doing. Now, that isn't true of all mortgages, but it certainly is true of a lot of them. We've got these little mortgage banking companies, they call themselves. There's a mortgage bank. It's actually a storefront on Main Street where you go in and sign all the paperwork, and they arrange the loan and all that, and then they sell the loan, and wouldn't be making the loan in the first place without knowledge beforehand of being able to sell it at a price that they can count on. So how much do they sell it for? What's it worth? We'll figure out how you think about that. How much is a company worth? Now, there's a question. It's got to be interesting, doesn't it? You've been in business for the last 25 years, time to retire, and you've got some bricks and mortar, and you've got some company goodwill, and you've got customers that are used to trading with you, and you want to sell your company. What's it worth? My goodness, is there a way to think about that? And the answer is, there better be, because it happens all the time. And, of course, it won't surprise you to learn that there is a way to think about that, and it involves the time value of money. How does inflation affect interest rates? You may have already learned something about this. If you've taken some economics courses, you know that there is a very good approximation to how inflation affects market rates of interest, and it just goes like this. The market rate of interest is going to be equal to the real rate of interest, something we call the real rate of interest, plus the expected rate of inflation. So if the market, actually, since you can't directly observe the real rate of interest, we should turn that equation around, shouldn't we, and solve for the real rate of interest. Since you can't observe that, you can't observe the market rate of interest. You also can't observe the expected rate of inflation. You can only observe the last year's measured rate of inflation, or some previous set of years' average rate of inflation. But that's the rule of thumb. Well, you're going to find out in finance that that's just, maybe you already knew this, I doubt it though. I went through my whole, believe it or not, I went through my entire PhD training in economics and never learned the exact relationship between the rate of inflation and the market rate of interest. It turns out it's a little bit different. The one that we just mentioned is a very good close approximation, but it is not exact. Well, if you are working in the field of finance in some way or another, and you're dealing with serious dollars, like hundreds of millions, nay, billions.
Little bits of percentage points.
Yes, close approximations are not going to be good enough, right? And so we're going to learn, well, how do you figure that out exactly? If someone tells you, never mind what somebody expects the rate of inflation is, here's what to use for the rate of inflation. Okay, then how do you calculate what the real rate of interest is that you're either getting or paying based on the market rate of interest that you actually pay or receive? So that's what that's about. Here on slide 5-3 then is just a recounting of what we would like to learn into our bones over the next 4 weeks. And when I say into our bones, now that doesn't apply to people who are just trying to get through this course with a passing grade. That applies to people who actually anticipate a career in finance of one kind or another. We're going to learn the terminology of the time value of money, so words you need to know the meanings of. We're going to learn to calculate future values and present values until we go blurry in the eyes. We're going to calculate interest rates that are implied by given future values and present values. We're going to learn to compute a bond's yield given its price and term to maturity. In another chapter, we're going to learn a lot more about bonds, and so this is just going to be a quick collision with bonds. Later on, we're going to have a full wreck with bonds in a chapter on valuing bonds. What does this word yield mean? Well, I put in here parentheses, rate of return. But one of the things we're going to learn is that there are all kinds of rates of returns one can think about. And it turns out that with bonds, there are actually 3 different yields that we learn how to calculate. The word yield generally refers to some money that you're actually getting. Okay, so we don't speak of, we tend to speak of a yield on bonds because bonds have a coupon payment, right? And we know that the coupon payment is an amount of money. But what is its rate of return yield? And there are different ways to think about that. So sometimes I dwell on this and dilate on it because a lot of students say, well, gosh, I know what a rate of return is, I think, and I think I know what an interest rate is. And what the hell is a yield? Well, it's just a word. It's just a word, first of all, but it does refer to some kind of rate of return. And we use the word yield because it's actually, it actually relates to some money you're going to get. Okay. And it depends on the price and term to maturity of the bond. We're going to understand that. We're going to understand the relationship between real and nominal cash flows and real and nominal interest rates. Now, in economics, I teach it every year, and we do make a distinction in economic talk and thinking about real values and nominal values. Some people just sort of understand that almost immediately without second thought. Other people languish over it and never can quite understand it. And we're going to make sure we understand it in this topic. Real versus nominal cash flows. And real versus nominal interest rates. We're going to understand how to compare interest rates. This is devilishly tricky. For different periods of time. There are a little bit of intricacies about this whole business of if you have an annual rate of interest, well, how does that come out if we want to convert that to a monthly rate of interest and all that? And you say, well, then just divide by 12, and the answer is maybe. We'll see how all that works. Okay, so here on slide 5-4, This is going to go by rather quickly. We'll encourage our interlocutor, fellow student Jake here, if he sees something that just immediately provokes a question, well, he should certainly ask it. But it won't surprise me if there aren't too many questions that come at this point. But I trust that there will be more later when we spend some time with our workbooks. $1 invested at interest rate R. Sometimes when you see a statement like that, it helps to just go ahead and put a number in for R, like 5%, for example. If you don't like to think abstractly, then put a number in there. Of course, when you put the number in there, you better represent it as 0.05 instead of 5%, because unless your program has been written such that it deals properly with 5% entered as 5, then you get the wrong answer. But 5% really is a fraction, isn't it? It's 0.05. So think of R as 0.05 there. $1 invested interest rate R will increase in value each period. Notice I didn't say how long the period was. The period, by the factor 1 plus R. Now, some people immediately say, God, I remember that word factor. I encountered that first in algebra, didn't I? I used to factor things. I used to hate factoring things, didn't you? You know, just had to factor these bloody... Yeah, Jake, you loved factoring things. Let's factor a few things. What does the word factor mean? Well, the way I always like to think about it is something multiplied times another something. The factor is involved in a product of terms. And so when we say the factor 1 plus R, you should immediately come to your mind, well, I'm going to multiply that times something, and if it's a factor. Indeed, that's exactly what you're going to do. And so then so for each period, the value will increase by the factor 1 plus R. So for one period, $1 grows into, if R is 0.05, $1.05. Yeah, so that's easy for one period. But what about more than one period? After T periods, its real value will be this mysteriously looking statement, $1 times 1 plus R raised to the power T. Now that's what that means when it says 1 plus R and you got that caret sign and then T. I use in these slides and throughout our discussions and talk about all this time anyway, I use the Excel formulations for doing this because first of all you need to know them, and secondly we're going to use Excel. And anybody that works in finance would immediately recognize that. They wouldn't scratch their heads and say, what the hell does that mean? No, they would immediately recognize it because they use Excel all the time. People who do finance know what that means. 1 plus R raised to the power T. Well, now, if T is 1, what do you get? You just get 1 plus R, because anything raised to the power 1 is just the anything. It's just what it was before. You do remember that. Now, if you always had trouble with the algebra of exponents, then you're just not going to like this at all. But if the algebra of exponents was always quite sensible to you, then this will appear to be something like child's play. Notice that I could just go ahead and remove the $1 times part, but since it is 1, and then I would just have left 1 plus R raised to the power T, wouldn't I? Right. Indeed, and sometimes if you see it written that way, and people say, what happened to the 1? And then they say, well, it's just 1. Don't worry about it. It's gone. It's just 1. So I just go ahead and write it out there because we can talk first about this in terms of $1. Then that leads us on slide 5-4 to the proposition of future value. And now we're getting more and more general. So we started out with a very specific idea, which seemed to make sense, right? 1 times 1 plus R, and if R is 0.05, that's $1.05, right? Then we go to a more general notion of, well, what if we have more than one period? What if we have T periods? And T, it turns out, is usually going to be an integer. 1, 2, 3, or 14, or 73, whatever. It's usually going to be an integer. And this is what's going to turn out to be a little bit confusing later on, because you can have fractional periods. We won't worry about that just yet. But for right now, let's just always think of T as being an integer, some countable number of periods. And then we get this general expression, which is the basic, I say, is the basic TBM relationship using compound interest. You shall emblazon this in your memory. It shall become you, and you shall become it over the next 4 weeks. And we hope therever after. Future value is equal to some present value times the compound interest factor, it's called. What is that? 1 plus R raised to the power T. Now you just sleep with that, think about it, dream about it, write it out, maybe scratch it with a needle into your forearm, whatever it takes. Because that is the heart and soul of time value of money right there. I can just see it throbbing as I sit here. Ka-thump, ka-thump. It is, it's throbbing for me. So let's see, how does that work? Well, let's just try it with $1. If I have $1 here, and for PV, that's the present value. How do I know it's present? Well, it's in my hand. I have $1 presently. And then somebody says, I will pay you interest at 5% per year. I said, fine. He said, if you give me your dollar now, then after the year passes, evidently in the future value of that $1, which will be what they owe me back, is going to be $1 times 1 plus 0.05 raised to the power, and if we're working in years, if that is indeed an annual rate of interest, T is 1, and I get $1.05. And so 1 year later, they need to bring me $1.05 and say, here it is. See? So the present value is the $1. The future value is what it grows to after I have interest compounded for T periods. Well, that was easy because T was 1. And let's see what happens using our old buddy algebra. Most people don't really think about it, but algebra is a Arabic word. Algebra. You didn't know that, did you? But those Arabs are smarter than you think. They, in fact, invented some of this stuff. And all this time you thought it was the Romans. No, the Romans were actually rather dense about this kind of thing. They had Roman numerals and could scarcely count their toes. But the Arabs, algebra. And so they came up with some of this stuff. And we get this. Oh, damn, that looks ugly, doesn't it? Well, it shouldn't let it bug you.
So to visualize what it really looks like.
All we did was divide the fundamental relationship by, we divided both sides of the equation by the compound interest factor, as it's called. That's what this 1 plus r raised to the power t is called. It's called the compound interest factor because we multiply times stuff. We just divided both sides of the equation by it. That's algebra, right? Everybody knows algebra. Remember algebra, you have these equations, and whatever you do to the left side, if you do to the right side, it's still an equation. Remember that? So if you kick the left side, you kick the right side, it's still an equation. If you spit on the left side, spit on the right, it's still an equation. So that's all we did. I'm trying to make this simple to people whose eyes naturally roll back when they see things like this. It's not anything beyond what you can do. That's all we did. And what do we get? Well, then we said we could just rewrite this by our friend algebra to solve for the present value if we knew the future value instead. And that's all we've done. And so what does it say? It says, well, you can write it this way, future value divided by 1 plus r raised to the power t. But lo and behold, through the magic of the exponential algebra, you could also write it as a factor in using negative exponent. Instead of the divider, you could write it as a factor. And this is where the eyes really start to flutter and people swoon and they say, God, I thought this was going to be finance, and here it turns out to be algebra. And I hate that. I never liked it. Right? But don't let it panic you. When I write it future value times, see that time, that's what the star means in Excel, times the 1 plus r raised to the minus t. So what the hell is confusing me? What does that mean? Well, evidently, 1 over 1 plus r raised to the t is the same thing as 1 plus r raised to the minus t. That's exactly what's going on. And it just looks complicated, but it's really not. When you put some numbers in and you see some numbers, and we're going to see plenty of numbers over the next 3 weeks after we get finished this week, it's really just not scary at all. And you do just have to remember that if I had x raised to the power t, then x raised to the power minus t is just 1 over x raised to t. And if you never learned that in the first place, well, then you can't remember it now. But I hope that somewhere along the line, like maybe when you took college algebra, you did learn that, right? And so don't let that panic you or anything. It's sometimes we write it this way with a divisor. Sometimes we write it this way as a factor, just depending on which is more convenient for the calculation we have in mind. Okay. All right. Well, what does it say then? By the present value of a future payment just is the amount you need to invest today to equal the future value available 10 periods in the future. And what I didn't have written there is if you are earning a compound interest rate R. Now you see, so you've got $1 today, that's your present value. How do I know that? That's because that's how much I would need to invest today, $1. If I want to have $1.05 1 year from now and somebody's paying me 5% interest per year. It's really not too difficult. Now, when we write this guy, 1 plus r raised to the power minus t, instead of calling it, as we did before, remember we called 1 plus r raised to the power t, what do we call that? We call that the compound interest factor. When we put it as minus t, which means we're just dividing it into 1, we call it the discount factor. It won't be the same number as the compound interest factor. It'll be the inverse of the compound interest factor, which means you just divide it into 1. So really, it looks terribly like rocket science to people who just don't do a lot of math from one day to the next. But after you get used to this and comfortable with it, it's just like, oh, this is boring. It's so easy.
Yeah, it's just you have to have a good command with that.
You do. And you will have the command, but what I'm just wanting to emphasize to you right now, if you're out there in online land and you're beginning to think I'm in over my head and we're hard to get started, you're not in over your head. You can multiply. you can divide, and that's all we're doing. We're doing nothing more than stuff that you've been doing since, I don't know, 4th or 5th grade. Right? So don't let it panic you. Whatever else you do, just say, okay, this is actually just multiplying and dividing. I've been doing that for years. Okay, and you're right there. The discount factor does what in English? It gives the value today of $1 payable in period T in the future, if you happen to be earning a compound interest rate of R. Okay? So, God, we've just covered miles on one slide in terms of the real core foundational ideas. Let's move to slide 5-5. We do have some terminology to learn. Learn it well, and it will serve you well. It'll come up over and over again in this course. It'll come up over and over again in the next course if you take it, financial management. And if you happen to be lucky enough to be good at this stuff and get a career in finance to make you rich, which you surely will be if you have a career in finance, these terms will be just household words. A level stream of future cash payments that continues forever, which is quite a long time, is called a perpetuity. It's called a perpetuity. Forever. How long does it go on? Forever. So let's take an example. I come up to you and I say, Jake, if you give me $1,000 today, I'll gladly pay you $10 a month forever. Would you be willing to do that?
Yeah.
Jake says he would. I don't know why he says that, but he does. He says he would. I'd have to do some calculations myself first, because I don't really know for sure yet, but I would.
I'm a young guy.
He figures he's young.
I'll live a little while.
In a little while.
$10 a month, $120 a year, so in 9 years I'll...
In 9 years he's in the gravy, right?
Yeah.
But this goes on forever.
Right.
Even after Jake dies, he can leave this piece of paper that says, I owe you $10 a month forever. Do you think? Go ahead.
What about when you die?
What about when I die? Well, there's a question. I'm the guy who owes the $10 a month. What about when I die? I better make provision for that, otherwise I'll be rooking somebody, won't I? I'll be having them, I'll be taking them. So, gosh, this idea of a perpetuity is rather strange, isn't it? It goes on forever. If I did give you such a piece of paper, so here's a piece of paper. Let me turn it around. I say, here's a piece of paper. It promises to pay you $10 a month forever. How much would you pay for that? Now there's a question, and soon enough you will know an answer to that question. But such an arrangement is called a perpetuity. Well, who on earth could enter into a contract for a perpetuity? I could see myself buying one because I could say, well, you know, I realize I'm going to die, but I can't leave this in my estate. Who could possibly pay a perpetuity? The answer turns out, even a corporation. It might issue one, but who would buy it? Nobody believes a corporation is going to last forever. What might last forever? You know, some kind of government. Indeed, the Bank of England has issued some perpetuities. They're called consols. They promise a cash payment forever. And people have bought and sold them. They're outstanding today. You can go buy a console today if you want one. All right, well, since it's so unlikely that anybody will have any truck in perpetuities, why do we bother with them? And the answer is because they give us a convenient way to think about this next guy, which is called not a perpetuity, but an annuity. An annuity of any kind, and there are different kinds, is a level stream of future cash payments that continues for a fixed number of periods. So not forever, but for some number of periods. So I might come to Jake and say, well, I'll tell you what, if you will just give me $5,000 today, which I need because I'm having a big party and I need to buy some cheeseburgers and I don't have any money right now, I promise to pay you $500 for the next 70 months. Would that be a good deal for you? How about, I misstated, I meant to say 10 months.
That's not a good deal.
Okay, so that might not be such a good deal. But what makes an annuity is a level stream of cash payments that are equally spaced. See, regular, equally spaced payments for a fixed number of periods. That's an annuity. Okay, well, if I did offer you such a thing, and it happens all the time, by the way, they're called loans. All right? If you think about it, what is a mortgage? A mortgage is just exactly that. A mortgage is somebody says, give me this much money today, so I go buy this house, and I will pay you for the next 360 months, $798 a month. Well, how much would you be willing to lend them under those conditions? Well, the answer is you would be, listen to this, willing to lend them the present value of that annuity. Oh my. So you could learn, and we will learn, or you'll fail this course, how to calculate the present value of any kind of annuity, and we will understand that in terms first of a perpetuity. That's hardly anybody has any trouble with perpetuities, but it turns out perpetuity is a very, very cool way to understand how to calculate the present value of an annuity. And annuities are so common, like you might trip over one on the way out of the room today. If you're buying a car on time, you are involved in an annuity. Where else do we encounter annuities? We encounter annuities when people who wish to retire buy an annuity. They go to a company and say, here's my life savings. I have $200,000. How much will you pay me each month for as long as I live? And the company says, well, we don't know how long you're going to live, but we will pay you this many dollars each month for the next 20 years if you give us that money.
What's the advantage of doing that?
Well, the advantage to the annuitant is that they know how much money they're going to have for the next 20 years.
We don't even worry about
Well, they do, but it's a lot less money than they're going to get. You see, they might be able to buy the annuity for $200,000, but should they in fact live for the full 20 years, they get a monthly payment of some fixed amount for the next 20 years that if you add it all up far exceeds $200,000.
So what's the companies? Are they trying to invest that money?
Ah, yes. Well, the company, the annuitor, is going to have to come up with some way to grow that $200,000, aren't they? Mm-hmm. Oh, yes.
Either that or they're just banking on you.
Either that or they're going to put out a contract on you. Right? They're going to just bank on it. They're going to make it happen. Interesting. It's very interesting. I met a guy at a party, I don't know, 3 or 4 or 5 years ago, who knows how long ago it was. And, we were just chatting and drinking our scotch and so forth. And he says, and I said, well, what do you do for a living? He says, I buy insurance contracts. He says, what do you mean? He says, I go around to people and buy their insurance contract from them so that they make me the beneficiary. I said, really? He says, yeah. He says, that's what I do for a living. He says, you work for a company? No, I'm an entrepreneur. That's what I do for a living. I go around and I offer people a fixed sum of money today for me to be the beneficiary on their life insurance. What a business. I wouldn't want him to live in the same town as I did, but, if I need some money today, I might be willing to do that very thing, right? That might make perfect sense to do the very thing. All right, well, let's move along here. The present value of a stream of future cash payments is the sum of the present value of each individual cash flow. Now, when you just look at it in words, it's a little hard to absorb, isn't it? It'd be much easier when we draw what's called a timeline diagram, and we see stretching out into the future. By the way, for me, the future always goes from left to right. How about you? I don't know, some people, maybe that makes sense, other people don't see it that way, but when I visualize time in months, they always move from left to right. I mean, for some reason, it's probably because we read left to right. I don't know what it is, but when I visualize time going forward, I visualize from left to right. So imagine these future cash payments. They might be all the same or they might be different. We just know that 1 year from the day we get a cash payment, 2 years from the day we get another cash payment, 3 years from the day we get another cash payment. Well, what if I wanted to know the present value of that future set of cash payments? Well, it turns out you can just add up the present value of each individual cash payment, calculated appropriately. Well, we'll learn how to do that. I just put it in there in words for you there so that you can have something to forget. So for a perpetuity, oh my God, look at this. We've got an equation. It says the present value of a perpetuity, remember what that was? That's a level payment that's periodic forever. You just take that payment, the PMT, divide it by R. What's R? Well, the interest rate that you would like to get, or that is promised you, or that is in the marketplace now. So if the payment were, let's say, $100, and if you looked around and you saw that the annual rate of interest these days for loans of this kind and that you can earn at banks and so forth is 5%, then what would be the present value of a $100 perpetuity, an annual perpetuity where you get paid $100 each year forever? $2,000 would be its present value. And so what if somebody offered to give you one for $1,000? That'd be a bargain. You say, geez, that is fabulous. If you happen to have $1,000 that you were looking to invest. You didn't want to go buy cheeseburgers, but you wanted to invest it. You say, well, that's fabulous. The rate of return in the marketplace is only 5% right now. Here I can buy a perpetuity for $1,000. That doubles my rate of interest. Yeah, I'm beating them over the head here. They should take out a contract on me. I'm such a ruthless financier. Right? So there it is. That's very simple. Now you can remember that, can't you? Sure. And it makes sense, too. Why does it make sense? Here's why it makes sense. Multiply both sides times R. in your mind. That leaves you with payment equals the present value times R, doesn't it? If you can visualize that. So what does that mean? That means if I knew a place where I could earn 5% per year, year after year after year after year after year after year, how much could I pay somebody if I happen to have an initial $100 to start with? Well, see, if I got $100 and the interest rate that I can earn is 5%, $5, right? Well, I could do that the first year, and then what I do the next year, I still got $100. I just gave them $5. I still got $100. I can earn 5% next year. So if I actually know a source where I can earn 5% per year, each year, year after year, forever, I could actually make a $5 payment to somebody forever, couldn't I? So it's very easy, the idea of perpetuity. You say, well, there is no such place where you can earn 5% per year, year after year, forever, is there? No, not really, but the idea is simple, isn't it? That's why the present value of a perpetuity can be written that way. When you write it that way as a division of the payment by the interest rate, it looks complicated and confusing, doesn't it? But when you multiply both sides by R and just recognize that, let's say, I don't know, let's say God says that he'll pay you 5% per year on $100 forever, right? Well, clearly, then you can pay somebody $5 a year forever. See, so that when we turn it around and divide back through the R, we get to the present value of the perpetuity. It's just whatever the present is, just whatever the payment is, the promised perpetuity. See, that payment is the perpetuity, isn't it? Divided by the interest rate that we're working with, that gives us the present value. That's easy to understand, and I want everybody to dwell on that for a while, and like just before you go to sleep or something like that, think about it and run some numbers or think about it until you just get so comfortable with that that it's kind of like, oh yeah, that's easy. Okay, because that is going to help you a lot to understand this guy, this next one. What's the present value of an annuity? Oh God, that looks so complicated, doesn't it? That's just, whoever came up with that must have been, I don't know, dated Einstein or something, right? They're just like, that's just incredible. That's complicated, isn't it? It is to me. I mean, I look at that and it just makes me want to retch or something. It's busy. Oh, bloody shit. It's just nasty. But now look what it is. If you multiply the payment through, what's the first term?
Taken over R.
Which is a perpetuity. Oh, wait. Oh, I understand the perpetuity. So we say the present value for an annuity that runs for T years. Remember that annuity is a level set of cash flows for T periods. You start out with a perpetuity and then you subtract something from it. Okay, so what is it that you subtract from? Well, guess what it is? Oh my goodness, when you multiply the payment through there again, to that term, the one over all that gobbledygook there, the first part of that gobbledygook is the perpetuity. It's the perpetuity again. But then it is multiplied by, and remember it's 1 over. It's something to do with the compound interest factor, but then there's an extra. Oh my goodness, all we've done is we've taken one perpetuity minus another perpetuity where the second perpetuity was delayed in its beginning of payment by T periods. How cool was that? Now, most people say, I didn't follow all that, Kimball. You're on that bike again, so I will. You start out with a perpetuity which lasts forever. Now, let's just suppose the interest rate's 5%, right? Just put 0.05 in everywhere you see R. And let's suppose that the annuity goes for 10 years, so you put in 10 for T. So how do you figure out what the present value of an annuity is? Well, you figure out what the present value of an annuity that starts today is, that lasts forever, right? And then you figure out what is the value of a different perpetuity. It doesn't start today. It starts 10 years from today. How clever was that? I just have always been fascinated by it. I'm just sitting around here thinking, when I first saw this, I said, damn, that's cool. That's so cool. How anybody, they took one infinity from another infinity to get a finite. Wow. That's why I say married to Einstein or dated him or something. I mean, like really smart. But that's really all that's going on there for an annuity. That's how I'm able to remember that. You say, you can't remember anything. You've told us this time and time again. It's true that I can remember that. I can say that in my sleep. Because why? Because it involves a concept that has always been true and always will be true and never could not be true. It's not a contingent truth. It's just true. It's like the Pythagorean theorem. I mean, that's just the very definition of a right triangle is the Pythagorean. So this is why I can remember it, because it's a concept. Well, I just want you to understand that this terribly complicated looking thing on slide 5-6 for the present value of an annuity is understandable. You don't just have to memorize it, in other words. If you recognize that it makes perfect sense. This is very understandable. If it isn't, and you think more about it, the perpetuity thing, that's very understandable. But when you think about the annuity and you recognize it's the subtraction of one perpetuity from another, where the thing you subtract doesn't start for 10 years, 10 years to be more precise, it becomes very intuitive to me. I love it, love it. Now, for an annuity, you can do a little algebra. That's all we did, right? It's just, okay, fine. You can calculate the future value of an annuity just by doing some algebra, that's all. That's just algebra. You say, well, is there some trick to that? Yeah, it's called algebra. It's not a trick. It's logic. Algebra is pure logic, isn't it? Algebra is just logic. Some people say it's death by logic, but it is still logic, right? Algebra just makes perfect sense. It couldn't be otherwise. There are a lot of pieces of math that don't seem to be perfect sense, but algebra just is logic, right? Okay, so we've got these two expressions. This one I can remember. This one I don't try to remember because I don't care. Yeah, I mean, I could always solve this from this one because I know algebra. I could work it out if you made me, right? If you forced me to do it, I could do it. It might take me a few minutes, but I could get there. Usually I don't do any of this because I use Excel whenever I want to do financial calculations. First I understand what we're looking at on these slides today, and then after I know for sure that I understand what I'm doing, then it turns out that I can use Excel's built-in functions to do all this kind of stuff, and I don't even have to worry about whether I get it right because I know Excel will get it right. But we will learn to do both the algebra of time value of money, and then we will learn to use Excel's functions, built-in functions, to do time value of money calculations once we understand what we're doing. Okay, so we're talking about time value of money, of course, and that's what the topic is in Chapter 5, and we'll occupy our time now for the next 4 weeks. Well, I guess we're halfway through the first week. We're nearly through, almost all the way through it, actually. So we've got a while with this topic. Let's just start at the top here. We're going to make here a clear distinction. I'm going to give you the truth and nothing but the truth here about the distinction and relationships between nominal values in financial theory and real values in it. You may recall, as I mentioned last time, that in economics, when we're taking some course in economics, we do all learn that there's a really easy and intuitive understanding of the distinction between nominal values and real values, and extend that to interest rates. And in the world of economics, where we don't need to be too precise most of the time, we just say, well, the nominal real rate of interest is equal to the real rate of interest plus the expected rate of inflation. You may recall that from one or another economics course that you've endured so far. And that makes perfect sense. So, you know, if somebody says, well, I'm going to enter into a debt contract with you, I'm going to pay you 10% annual rate of interest if you'll lend me money. I'll pay you 10% per year, and you scratch your head for a minute and say, now, wait a minute, I know that the rate of inflation is likely to be 3%. So by the time I get my money back at the end of the year, it's going to buy 3% less than it would have before. So when he says he's going to pay me 10% rate of interest, it's really only 7%. And everybody sort of latches onto that and understands the sensibility. And there's nothing wrong with that. That is approximately true. Well, here on slide 5-7, we're going to find out what is absolutely true. Okay, and it turns out not to be a big difference, but it is when you're dealing with large amounts of money. So in the rate of inflation, well, first of all, the nominal value of $1 is just $1. That's what nominal means in name. Nominal. To name it, it's $1. $1 is $1. That's always $1. But inflation, if we have the phenomenon of inflation, which can be, for our purposes, just thought of as an increase in the average of all prices in the economy. So it's rising over time. And it's a sustained increase. It's not like it goes up one time and then stays there. It just keeps creeping up over and over, year after year, at some rate of growth. And in the United States, for the last, 10 years, something like that, the average rate of inflation in the United States, at least as it's measured by the Consumer Price Index, is, somewhere around 3%, 2.5%, 3% per year, whatever it is. So we'll use 2% because 2 is a nice number. So when we talk about nominal values, we're talking about just the actual dollar values that you see out there in markets. When we talk about real value, we're talking about what those dollars will buy after you consider the effects of inflation. So the next bullet we see, it says if the rate of inflation is I, then let's just say, to stipulate for an example, so we can use a numerical example here, if it's 2% per year, then it would take $1, now we can do a little algebra here, times 1 plus 2%, or $1.02, 1 year from today to purchase something that costs $1 today. Everybody understands that, right? And when you write it out in algebra like this, I know some people get nervous, but it's really just multiplication and very simple logic. So $1 times 1 plus 2%. And of course, if you're really going to do the math, you have to write it as 0.02, and 2%, you get off a couple of decimal points, but if you write it as 0.02, which is the way you would write it in Excel, Excel can handle numbers that you put percentages on, but it's easy to get confused. It's easy to get Excel confused. Excel just does what you tell it to do, and sometimes you'll run into some calculations later in this course where you'll be off by a factor of 100. And what will have happened is Excel will have misinterpreted something that you put in there, and it will have thought you meant percent when you didn't, or vice versa. But anyway, you get the point. So, if the nominal rate of interest is, we'll designate that R sub n, just to give it a name. That's all we're doing, give it a name, a variable name. If that's 2%, that's the nominal rate. And the rate of inflation, the actual rate of inflation, is 2%. Notice we don't talk about the expected rate of inflation here, because whose expectations would you be talking about in the first place, and who has any idea in the second place? And so in finance we tend to talk about an actual rate of inflation, an assumed rate of inflation, or an historical rate of inflation, whatever. We don't mess too much around in finance talking about expected rate of inflation. That's sort of economic thinking. We just say, well, if the inflation rate is 2%, and the nominal rate of interest is 2%, nominal just meaning what you see out there in the marketplace. So you can observe the nominal rate of interest, can't you? Then what would be the real rate of interest?
Zero.
Well, it has to be zero. You know that. Has to be zero. So if you lend somebody $100, let's say, for 1 year, and they say, I'm so generous, I'm going to pay you 2% rate of interest, which would be pretty generous these days, as it happens, for 1 year alone. I mean, that's not bad. 2%, and the rate of inflation is 2%. Then what's going to happen on each dollar you borrow from them? Well, they're going to pay you back $1.02 with principal plus the interest that you get back, and lo and behold, you're going to go to buy something real and find out that what used to cost $1 now costs $1.02. And so how much interest did you really earn? Nothing. Everybody understands that. Well, what does the math work out to? Well, in the third bullet there, it says that would mean that $1 times 1 plus, now I've used R sub R. What does that stand for? That's the real rate of interest. Would have to equal $1 times 1 plus R sub n, the nominal rate. And then look what I've done. This should look, if you've done your homework and been reading and thinking about discounting, remember discounting? I'm dividing that by 1 plus I. So I'm discounting the nominal rate, as it were, by the rate of inflation. You see that? It looks like the same thing. It's like the exponent is 1 because there's only 1 year involved, right, on the 1 plus I. I didn't put the caret sign 1 up there since it just left. I could have. It would have been exactly the same thing. And so this begins to look like, well, this is kind of like discounting, isn't it? And so it makes sense to us. And in fact, if we did study economics and remember anything about price indexes, you might remember that you get a real value from a nominal value by dividing the nominal value by the price index number, don't you? And what is the price index number? Well, we know that the base year is 100. There's your 1. And then the rest of the number is the I part. I mean, it all hangs together. It makes perfectly good sense if you think about it long enough. So even though that was a very strange thing to write there, where it says that this means $1 times 1 plus R sub R equals $1 times 1 plus R sub M, divide that whole thing by 1 plus I. That's the sense of it. Well, then, if you just rearrange that, which is the way, the understanding of it for me is the second bullet. The best way to write it for general purposes is the third bullet. For me, every time I look at the third bullet, I say, well, how would I ever understand that? It's true, but why is it true? Our good buddy algebra is why it's true. The sense of why it's true is the second bullet. The algebra of how you can write it, just algebra. That's the way I look at it. Now, other people might look at it completely differently. They look at the third bullet and say, oh, that makes perfect sense. For me, it never did. I always had to look at the second bullet to get to the third bullet. But however your mind works is fine by me. The end result is you will see it written this way in red in the third bullet, which says 1 plus the nominal rate of interest is equal to 1 plus the real rate of interest times 1 plus the rate of inflation. That gives the relationship exactly between the nominal rate of interest, R sub n, and the real rate of interest, R sub r, and the rate of inflation. Now, the earlier thing that we talked about, which was the approximation, why is that just an approximation? Well, the answer is because, do you remember in algebra what you get if you do this multiplication of these two factors on the right-hand side? You get the first, the outside, the inside, and the last. Remember that? Foil. Yeah, see, J.K. remembers that foil thing. That's how I remember it, too. So you multiply 1 times 1, that gives you 1. That's the first, right? Then you multiply 1 times the outside, or the 2 outside, which is 1 times I. So you get I. So now you got 1 plus I, right? Then you do the inside, you get R sub R times 1. That gives you the R sub R. And then finally, the last term is R sub R times I, which, if these are fractions, as they are, like 0.02 and 0.02, gives you a very small number, doesn't it? It gives you 0.004, doesn't it? Something like that. Well, that's not very much, is it? Well, all we're doing when we do the earlier approximation is dropping that piece off.
Oh, okay.
And that's why it's a good approximation, so long as the real rate and the inflation rate are very small numbers. And so that gives you not only the intuitively sensible economic interpretation that the real rate of interest plus the expected rate of inflation is the nominal rate of interest. You're just dropping off that cross product of two fractions. But that won't do in finance. Can't drop that off. Because when you multiply what is it? 0.02 times 0.02, 0.0004, right?
No.
Do I get 3 zeros?
Yeah.
I've never been any good with zeros, but I think you get 0.004. Well, multiply 0.004 times a billion, see what you get. It's more than chump change. So that's why we can't do without it in finance. So emblazon this in your mind if you can. If you can't, well, then you can look it up. On slide 5-8, this is important in finance. Always discount, when you're doing discounting of a nominal future cash flow, you must use a nominal interest rate in the discount factor. Do not mix real and nominal. You will get hash. You will get the wrong answer. You will get misleading answers. People do this all the time who are not astute in the theory of finance. That would be lawyers. They frequently have a tendency to want to do this. If you don't watch them, if you're doing something that involves finance with lawyers, you have to bring them back to reality and remind them of this stuff. But always use nominal discount rates with nominal cash flows. So where would I get a real cash flow anyway? Well, that's a different story. Everything's nominal that you can observe, isn't it? Everything that you can actually see is nominal. So somebody might say, where do I get a real cash flow? Well, somebody might have done some analysis where they discounted or they adjusted nominal future cash flows for inflation and then wanted to discount them using a nominal rate of interest. And actually what they've got is a real cash flow out there already. You begin to see what's possible if you think about it. So never mix nominal and real values or nominal and real interest rates in the same calculation. Just don't do it. Why? You'll be wrong, that's why. So I'm just warning you off a common mistake. On slide 5-9, this is very interesting stuff here, and very confusing, but we'll get through it somehow. Interest rates for periods of time less than 1 year are often quoted as annual percentage rates nonetheless. Okay? So, let's go through the paces here a little bit. If the monthly rate of interest happens to be 2%, well, what does that mean? Well, that means that we've got some kind of loan going on here, and the participants have agreed that interest will be paid monthly. It's due monthly, so you get a cash flow of interest every month. Suppose it's 2%. Then what is called the APR, or annual percentage rate, see how it's cleverly named, the APR, is 2 times 12, 24%. Okay? If the daily interest rate happened to be 0.015%, that's 15 thousandths of 1%, right, per day. So we're compounding daily for some reason. We've entered into a financial arrangement where interest accrues daily. Can you think of anything where that happens? Try your credit card. Your credit card uses a daily interest rate. It gets you coming and going. That's what they do with credit cards. After all, they're pretty risky, unsecured loan. The APR would be calculated as 0.015 times 365, since that's how many days there are in a year. That gives you 5.475% APR, annual percentage rate. Now, the thing I need to point out to you is that this doesn't make any sense. You say, why not? It makes perfect sense to me. Well, evidently it makes perfect sense to lawyers, because as it happens, the APR is a legal definition that's based on simple interest, not compound interest. It ignores compounding if you do it this way. Well, guess what? They passed a truth in lending law some number of years ago and defined the APR this way in terms of monthly and daily rates.
They defined it using simple interest?
Yes, it's basically a simple interest definition. Because, see, if it's going to turn out that you can just multiply 2% a monthly rate times 12 and get the APR, it must be that you're just doing simple interest month by month. And same thing with daily. And so the lawyers in their, whether it was ignorance or their quest for simplicity, which seems quite unlikely, I guess that leaves with ignorance, they came up with a law that says if you quote somebody an APR, but you're actually accruing interest at a periodicity less than a year, here's how you have to represent it. Just like this. Well, that's simple interest. Well, nobody in the world of finance uses simple interest because everybody understands that simple interest is just not right. You might say, why isn't it right? I couldn't give you a good answer. It just isn't done. Any kind of interest in finance is going to be compound interest. Interest earned on interest is what the compounding is all about, which we've seen. You'll read about it in greater detail. I don't go into it in great length here in the slides because, after all, you can't read. But we do go into it in the textbook in a very compelling, straightforward way to show you what compound interest means and show you examples after examples, and you get blurry-eyed with it, but there it is. Well, that's the world of finance. The world of finance uses compound interest, not simple interest. So, once the APR got defined legally in the United States, see, truth in lending law was a good law, really, because it used to be that all these different ways. This was quite a while ago. It's even older than I am, which is quite old. They used to, vendors and lenders and people involved in selling people stuff on credit, all kinds, they would quote interest rates all different ways. And the argument was made, well, people are just being bamboozled. They don't understand at all what they're getting themselves into. They don't understand anything. And so, to the lawyers' benefit, and the politicians, who are largely lawyers, benefit and praise, they did say, well, we'll standardize this so that people will know what they're being told when somebody tells them you're going to be paying a 10% APR here. And so they did. And since there are all kinds of lending contracts that involve lower than 1 year periodicity, this is how they define it. Okay. Well, that's not compound interest. That's simple interest. So what is the answer to this? Well, the answer is what we call in finance the effective annual rate, the EAR. The EAR, the EAR, uses compound time value of money to analyze an interest rate quoted for a period less than 1 year. Let's see how it works. On slide 5, page 10, the relationship between the annual percentage rate, as we've seen it defined, and the EAR, the EAR, is given mathematically as follows. We first define MPRs and DPRs. It's usually days or months that we're concerned with. We're hardly ever concerned with seconds or anything else. Well, it could be, right? It could be. It would be a true Shylock that compounded interest about the second, right? That's getting awfully close to continuous compounding, which takes you into the exponential function, by the way. Just for those of you who are so mathematically inclined that you're beginning to think along those lines, that's it. That is what happens. But you could compound interest by the second, and by the tenth of a second. Then it gets ludicrously close to continuous compounding, which takes you into the E function, the exponential function. And if you go far enough in economics and learn enough calculus, you will do that, because you will use E functions instead of these clumsy 1+ things, because it works out so smoothly when you do. And if there's the promise of nothing if not smooth. So, but anyway, you saw back on 5-10, the monthly percentage rate, the NPR, we will define that as the APR divided by 12, which is just what the law does. The DPR, the daily percentage rate, is just the APR divided by 365, which is what I showed you on slide 5-9. That's what the law says you will do. Well, then, once you got those definitions, what is the EAR, the effective annual rate, which is the truthful, actual compound rate associated with any particular APR if the periodicity that you're having to work with is monthly or daily. That's the real issue. Well, here it is in all its glory. It looks just blindingly ridiculous. 1 plus the effective annual rate will be equal to 1 plus the defined APR divided by the periodicity M. Now, I've gone to variables because we don't have to restrict ourselves to days or months, so we could do whatever we want to. We do weekly if we want to, for example. So that's why I introduced the M. Okay? But here's the relationship. It says 1 plus, take the APR that's being quoted, divide it by whatever the periodicity is, days, months. Right? Notice that if M is 1, what do you get?
1 plus APR.
Yeah, it's the same thing. So the EAR will equal the APR when we do an annual. Well, better. That only makes sense, right? But if M is 12 because we're doing monthly, then you could write APR divided by 12. M, that's the MPR, so you could write MPR there, right? Well, but you have to raise it to the exponential M, whatever M is. So in this case, if we were converting a monthly APR to get an effective annual percentage rate, that is the real one, the one that's really the compound rate, you would be taking the APR, whatever it is, divided by 12, and then you have to raise that whole thing. So you raise the whole 1 plus the thing there to the power 12, in that case, if M is 12. Okay, so if that's true, and it is true, it's just taking account of the compounding. So because the interest is, if you've got a monthly contract, if you're paying interest monthly, and you're paying compound interest, you're going to be paying a monthly rate, and to get the compounding, you do the raising of the tower. See, that's really, we've just gone back to the fundamental time value of money equation, haven't we? That's all we've really done. So don't let this bamboozle you. If it's bamboozling you, you have to go back to some earlier slides. It's really just building on what I told you. You have to blazon in your mind that the future value is equal to the present value times 1 plus r raised to the power t, whatever t is, right? That's all it is. So if you ever understood that, well, if you didn't ever understand that, you're hopelessly lost by now. You don't understand what comes after. So you've got to get that early for a second. But once you've got 1 plus the E or equals 1 plus the APR divided by M raised to the power M, you've got the next bullet. By what? Algebra. Good buddy, algebra. Good for him. And what do you suppose algebra means? You can look that up. I think it probably is with a J. Who knows what it is? Algebra. If you look that up, I think it's, we know all is V. I don't know what algebra is, but I bet it's something like the computing or the reckoning or something. Something like that. It's going to be something like that. We could look it up in just a heartbeat if we had our computer set to an appropriate web page. Anyway, so those of you who are just terminally inquisitive can look that up this evening. I will myself if I remember to, but I'm suffering from CRS, so it's hard to say. The APR is a legal definition that is based on simple interest, not compound interest. We already learned that. The effective annual rate, or EAR, uses compound time value money to annualize an interest rate quoted for a period less than 1 year. Okay, that's the word's sense of it. Now, we'll have some problems on this in our workbook, and you'll get used to it. It'll make sense. Now, the first time you go to sit down someday in the future to buy a house, and you're going to take a mortgage, right? You're going to get a mortgage. You're sitting there across from the lender in a pile of paper that's, I don't know, 5 or 6 inches thick. They're going to come across this one piece of paper. And on that piece of paper, which you must sign to signify that you have understood, of course, most people don't even read it. Fewer people still understand it if they did read it. But by virtue of taking theory finance, you will know what it says. Here's what it's going to say. It's going to say the APR that you will be paying for this mortgage is 5.25. The effective annual rate that you will be paying for this mortgage is, and what's it going to be? Higher or lower? It's going to be higher. And you're going to say, oh, I got that. I understand all that. Ordinary person's going to say, let's move on. let me sign it. I'm eager to get the keys. All right. So but that's what's going on because of this distinction now between the legally defined APR and the effective annual rate that goes along with any particular APR. When the periodicity is like with a mortgage, what, monthly? So you see the same thing with a car loan. Go buy a new car. You're going to see that same piece of paper, only because they're not usually talking about $200,000. Nobody cares too much whether you pay any attention to that or not. And you just sort of sign it. So here, sign all these papers, and they don't even attempt to tell you what that's about. The truth is, neither do they when you're doing a mortgage, because mostly the people doing the paperwork with you when they're doing a mortgage have no idea what's going on either. But you will know. Maybe you could give them a tip when you get to that point in your life, or not. Well, we have exhausted all the slides that I cared to render for Chapter 5. We've certainly not exhausted everything one needs to know. When I use the word know, I just mean remember. If you remember, and say what is learning? Well, you remember something. Could be you remember something if you know something, right? You remember it. So there's that. Or if you've learned something, then you know how to do something that you didn't know how to do before. But we're certainly a long ways from that. We're going to give that big workout over the next 3 weeks. And then the other thing that constitutes learning in my world is you've experienced something you've never experienced before. That's what constitutes learning in my world. You either remember something that you never even heard of before, but somehow you know it now. You remember it. That's where I fall off the log. I don't remember much. Or you know how to do something that you didn't know how to do before. Now I know how to do a lot of this stuff that we'll see in the workbooks, and somehow or another I can get through that. But I've had experiences that, and you've had experiences that constitute learning that other people haven't had. I always like to use this example to make that point. Probably wondering why am I making the point at all. It's just because I like to. Have you ever walked across the Golden Gate Bridge?
Yes, actually.
And it turns out Jake has. Would you say that is an experience that taught you something that you now, there's something about that others who haven't don't have?
Maybe.
I would. I definitely would.
It's been a long time since I've been there.
I walked all the way across the Golden Gate Bridge, and that's right, San Francisco Bay. And if you ain't had that experience, it's something that you just don't know anything about. One of the things that you don't know about it is that you can move the bridge. You can make the bridge move. So you got to be kidding me. It's true. About, I don't know, every, 50 feet or so, we've got those four cables that are about probably 3 inches in diameter. There's a cluster of 4 of them that go up and hold. They spin the bridge roadbed from the big cable that's literally 3 feet in diameter or something like that. If you get out there, I don't know, 100 yards into the bridge where those rising cables are long enough, you're way back at the beginning where they're only 2 feet long, not much happens. But if you get out there where they're 20 feet, 30 feet, and then 50 feet, and then 100 feet, somewhere, if you take the heel of your hand and wrap it, it starts to vibrate. You can move the bridge. That was always fascinating. It just fascinated me. So that's an experience. I learned that, and you only get that from experience. I can tell you about it until you walk across the bridge. You won't really know. So we're going to learn in the next 3 weeks how to do some things that we don't know how to do right now, I expect. They're going to involve all manner of time value of money calculations, some which you have encountered before, some which you can't even imagine anybody would have ever thought of before. But we're going to get good at it. And if you get, I promise you, trying to incentivize you now, if you get good at it, if you get good at time value of money calculations, you will raise your market value enormously. And if you don't quite get it, maybe you should go into marketing. Off we go then, unless you have a question, Jake.